Based on the syllabus, today we are going to cover the last section of chapter 9. It's also the last section of hypothesis tests. So let's go to our note. Section 9.3, two dependent samples. We might remember on Tuesday, we went over the definition of two independent samples and two dependent samples. And we can look at the definition of two dependent samples one more time. The definition is given in section 9.2. Right here. Two samples are dependent if the sample values are somehow matched, where the matching is based on some inherent relationship. That is, each pair of sample values consists of two measurements from the same subject, such as before and after, or each pair of sample values consists of matched pairs, such as husband and wife data, where the matching is based on some meaningful relationship. Caution: dependence does not require a direct cause or effect relationship. So that's the definition for dependent. The two samples, the values from the first sample, somehow are paired or correspond to the corresponding values in another sample. So that's the definition for two dependent samples. Before and after, husband and wife, we'll see some examples involving those relationships. Let's go to 9.3. And what do we do in 9.3? We still do hypothesis testing, but this time we are going to test the claim regarding the mean of differences of two samples, two dependent samples. Let me explain. So let's say we have two populations, population X and population Y. And from population X, we are going to draw a simple random sample with size n. So we have values x1, x2, and so on, x sub n. Sub n here represents the number of values in the sample. So that's the sample size of the first sample. And we are going to draw a simple random sample from variable y, from the population, second population as well. And the sample can be written as, sample values can be written as y1, y2, y sub n, have the same size. And those values are those values are matching. For example, if we let x1 be the data, some, maybe blood pressure, right? Blood pressure of one subject, and y sub 1 could be the blood pressure of the same person after a certain treatment, right? To see if the person had a high blood pressure after treatment, would the blood pressure drop. Or we can let x sub 1 be the IQ score of the husband, and let y sub 1 be the IQ score of the wife of the same couple. Those two are same couple. They are married. So x1 is the IQ score of the husband. Y1 is the IQ score of the wife. They are a couple. And these two are a couple, and these two are a couple. So those values have a matching relationship. The relationship either inherent or meaningful. All right. So now we are going to use x minus y. We are going to use x minus y. and to create a new population or new random variable. And from the new random variable, if we see x minus y as a new random variable, then we would have x1 minus y1, which is d1. Okay, yeah. So we use the first value in the first sample to minus the first value in the second sample. We would have d1 as the first value from the sample we are going to have from the population D. And if we let x sub x2 minus y sub 2 be d sub 2, then d sub 2 would be the second value. And so on and so on. We use x sub n. We have x1 minus y1 is d1. xn minus yn would be d sub n. Yeah, if we take the differences of all the corresponding values, all those paired values from the two samples, we would have another sample. We use d sub 1, d sub 2, and so on, d sub n, to represent the values in the new sample. And that sample, we see that sample as a sample from population D. Yeah, I always use a random variable to represent the population. And D is x minus y, population x minus population y. Depends on how do you interpret. For example, earlier we have x is the IQ score of the husband, y is the IQ score of the wife. Then D would be the difference of the IQ scores of the couple. Yeah, we use the IQ score of the husband to minus IQ score of the wife, and it will represent a population. Yeah, the population contains all the differences of the IQ scores of all the couples. You know what I'm saying? Yeah. So if we let mu sub d, yeah, again, we want to see D as a population, okay? It maybe doesn't sounds like a population compared with X and Y, but it is a population. So we use mu sub D to represent the population mean of D, the mean of the population D. Then today, this section, we are going to use the hypothesis testing method and the confidence interval method to test a claim regarding the mu sub D. So that's the purpose of today. That's what we're gonna do today. Yeah, let me highlight some important elements in this part. Yeah, it does involve two populations, and the two populations are dependent. From the first population, we have a sample with size n, and from the second population, we have also a sample with size n. And if we take the difference of each matched pair, since x and y are dependent, so those values have to be matched. But again, yeah, very important. They have to be matched. x1, y1 matched, x2, y2 matched, x sub n, y sub n matched, the same based on the same relationship, either inherent or meaningful. And then we take differences of those values. We use x sub I to minus y sub I is from 1 all the way to n. Then we would have a sample with size n, and the values in the sample can be are denoted as d sub 1, d sub 2, d sub n, and that sample is the sample we use to test the claim regarding mu sub d. And what is the mu sub d? Mu sub d is the population mean of the differences of the pairs. Yeah, we have a formal definition for mu sub d right here, notation-wise. Let's go through those notation. We use d to represent individual difference between the two values in a single matched pair. Yeah, as I did earlier, d sub 1 is a difference of x sub 1 and y sub 1. Same couple, husband score IQ score minus a wife's IQ score, or the person's blood pressure before the treatment minus the blood pressure after treatment, right? It's the difference. D represents the difference between the paired values in the two samples. And mu sub d, we mentioned mu sub d. Mu sub d is the mean of the differences d for the population of all matched pairs of data. If we see D, the capital letter D, as a population, yeah, as I always use the variable D to represent the population, then mu sub D simply is the population mean of capital letter D, variable capital letter D. In the example of a husband and wife IQ score, capital letter D represents the difference of couples IQ scores for all the couples. Yeah, for all the couples. And the D bar, when you remember, you would remember X bar, right? X bar is the sample mean, and D bar here also means sample mean. It is the mean of the differences. Yeah, D bar actually is the average of D1, D2, Dn. Yeah, we add up D1, D2, we add up D1, D2, and Dn, and then divide by n. So D bar is just the mean of the sample, D1, D2, and Dn. S sub D is the sample standard deviation of the sample. Yeah, this sample, okay? Yeah. S sub D is the standard deviation of this sample. And N, of course, is the sample size, or number of pairs of sample data. Let me know, do you have any questions about those notations? Especially, what does mu sub D represent? Any response will be appreciated. Yeah, I'm trying to explain what we do in this section. In this section, we are going to test the claim regarding mu sub D. Yeah, we would have to really understand what is mu sub D, right? Yeah, what is mu sub D? Taking notes? No, okay. No questions. Thank you, Charlene. Melinda has no question. Kelly has no questions. Okay, so I assume is clear, right, so far? All right, very good. By the way, you can take a screenshot, right? If you take notes, take a screenshot, leave those as pictures. That's what I would do if I take an online class. And we are going to apply 3 different methods to test a claim regarding the mean of differences for the population of all matched pairs of data, or mu sub D. The 3 methods are p-value method, critical value method, and the confidence interval method. What we need to know is the 3 methods are all equivalent. In a sense, all the 3 methods would give us the same result based on the same sample. Yeah, so this conclusion does not hold for proportion, right? If you go back to 9.1, p-value method and the critical value method are always equivalent. but confidence interval method is not equivalent with them. But when it comes to testing population mean, all the three methods are equivalent. They would give us the same result based on the same sample. So let's see what requirement the sample has to meet in order for us to be able to apply those methods. Okay, yeah, the requirements include 3 requirements. The first one, the sample data are dependent matched pairs. Yeah, very important, matched pairs. Second requirement, the matched pairs are a simple random sample. Yeah, it says the D, the green sample, D1, D2, Dn. Yeah, the second requirement requires this sample be simple random sample. But if the if this one, x1, x2, xn are simple random sample, and this is also simple random sample, and you take the difference, will guarantee D1, D2, Dn is also simple random sample. That's the second requirement. Third requirement is the requirement for central limit theorem. Then we can assume the sample mean is normally distributed. So here, either or both of these conditions are satisfied. The number of pairs of sample data is large enough go beyond 30, or the pairs of values have differences that are from a population having a distribution that is approximately normal. And we will see a question regarding this sentence. Robust against. We'll talk about that later, okay? About normality, it requires D to be roughly normally distributed, or the sample size is bigger than 30, right? In fact, if X is normal distributed, Y is normal distributed, and D should be normally distributed. Okay, so yeah, when we work on the Pearson assignments, they will state the 3 requirements and make sure that we are able to apply the p-value method, critical value method, and the confidence interval method to test the claim. Important thing about the hypothesis test for mu sub d is what type of distribution we are going to is going to involve. All right, yeah, t distribution. Okay, t distribution. When we talk about 2 samples, but they are dependent, and we are testing the claim regarding mu sub d, we are actually only have 1 sample. Yeah, seriously, we only have 1 sample. So the hypothesis test about mu sub d is simply a t-test. Is a simple t-test. It's just a t-test, okay? T-test. The reason is because we are testing for mu sub d, then we assume we do know mu sub d, of course. When we do not know mu sub d, we would not know the value of sigma sub d. So we would have to use S sub d to replace sigma sub d. So the statistic will be t distributed instead of normally standard normal distributed. So if you go back section 8.3, yeah, probably you would see how do we test a claim regarding population mean. Yeah, this section actually in essence the same with that section. It's just that before we actually tested the mu sub d, we have to do some work. What work? We have to find out what is d sub 1, d sub 2, d sub n. We have to find a sample. We have to make up the create the population capital D and find a sample. In essence, this section it just involves a simple t-test. And since not yesterday, on Tuesday, when we do 9.2, the whole time we were doing p-value method. So today, all the questions we are going to practice on are going to apply critical value method. All right, yeah, it's also required by the Pearson assignment. If you go to 9.3, yeah, most of the questions requires you to use critical value method. So we are going to practice critical value method and a confidence interval method. Let's look at some multiple choice questions first. Number 1, which of the following is not a principle of making inferences from dependent samples? Not. Okay. A, the t-distribution serves as a reasonably good approximation for inferences from dependent samples. I would say it's correct because we are using a t-distribution for the hypothesis test for mu sub d. Option B, there is some relationship whereby each value in one sample is paired with a corresponding value in the other sample. Yeah, that's the requirement. The two samples are dependent. And option part B actually describes what is the dependency between the two samples. There's a relationship exists. Option C, testing the null hypothesis that the mean difference, mu sub d, mu sub d equals to 0 is not equivalent to determining whether the confidence interval includes 0. Testing the null is not equivalent to determine whether the confidence interval includes 0. Let's look at D. The hypothesis test and the confidence interval are equivalent. Yeah, we mentioned that in the sense that they result in the same conclusion. A, B, D are all correct. C is incorrect. Testing the null equal to 0. So that means it's not equivalent to determine whether the confidence interval includes 0. Mean difference. Let me see the confidence interval. Mu sub d if it doesn't include 0. Oh my gosh, we are looking for not correct. Yeah, they are equivalent, by the way. Okay, they are equivalent. Yeah, as I said earlier here, the three methods are all equivalent. So when we test the null mu sub d equals 0 is equivalent to if we consider if the interval includes 0 or not. So it says not equivalent, so it's wrong. It's wrong, so that's the answer we're going to choose. Okay, I kind of got lost just a little bit just now. Are you guys okay with part C? We should choose part C because it is equivalent. It is supposed to be equivalent. We are choosing the incorrect answer. Okay, awesome. Perfect. So that's the question number 1. Question number 2, multiple choice question. Which of the following is not They like to do this, right? Not a requirement of testing a claim about mu sub d. The mean of the differences from dependent samples. A, the degree of freedom are n minus 2. Well, is wrong. Remember, it's a simple t-test. And the sample D, D1, D2, D sub n, the sample size is n, and the degree of freedom supposed to be n minus 1, not n minus 2. So A is incorrect, okay? A is incorrect. A is incorrect, then we should choose A. Well, let's spend time to look at the BCD as well, since we're already here. B, the sample data are dependent, yes. C, the samples are simple random sample, yes. D, either the number of pairs of sample data is larger than 30, or the pairs have differences that are from a population having a distribution approximately normal, or both. Yeah, those are the 3 requirements. We went through the 3 requirements earlier. The degree of freedom is n minus 1, okay, not n minus 2. It's n minus 1. We do start from 2 samples, but after we take the differences, we will end up with 1 sample only. This is about 1 sample, so it's a simple t-test. For simple t-test, the degree of freedom is just the sample size minus 1, not minus 2. Example 3. What design principle is stressed for experiments or observational studies? Experiment, you apply treatment, like a treatment group, placebo group. Observational, you do not apply treatment. You just observe, either observe right now, right here, or observe data from the past or from the future, So what design principle is stressed for both, for either experiments or observational studies? Let's read the questions. A, when using paired data, keep the sample very small in order to keep the data manageable. I don't think that's a good idea, because if the sample size is too small, then it's not going to be representative. We require the sample to be simple random sample, then they could be representative for the population, right? So I don't think A is a good idea. Let's look at the B. Using dependent samples with paired data. Use dependent samples with paired data is generally better than using 2 independent samples. Okay, so that's the B. C says using 2 independent samples is the best choice for accurate results. So B and C kind of state 2 different opinions, right? B says use dependent samples with paired data is better than using 2 independent samples. C says using 2 independent samples is better for the purpose of accurate results. So, I know that when you actually apply experiment, you randomly select subjects and you divide the subjects into 2 groups. One group is a treatment group, the other is a placebo group. Yeah, that's the way we normally do the experiment. But if it's possible, we can use the same group. Actually, if it's possible, we can use the same group of subjects and test the same subject before the treatment and after the treatment. It is actually better. than two different subjects. So I would say B is better than C. If it's independent, sometimes the two independent groups, sometimes they have not much similarity that you really can compare the treatment, the effect of the treatment. And part D says the methods for dependent samples can be used for any matched pairs. The methods for dependent samples can be used for any matched pairs. Methods for dependent for any matched pairs. There's any example that we cannot use this method? So this method is taking difference, all right? It's taking difference. If the difference of two matched pairs doesn't make any sense, then the method doesn't work. For example, the grades. We have a group of students, they have grade A, B, C, D, after taking a program, their grade changes, right? They have different grades like A, B, B. But you take the difference, remember they are not numerical. So the difference doesn't make any sense, right? So in that case, the method doesn't work because this method only works when difference is meaningful, like IQ scores or measurements. Yeah, we learned four what is that called? Ratio, interval, 4 level of measurements, nominal. Yeah, A, B, C, they are ordinal. Yeah, so the differences for like A minus B really doesn't make sense. So D is wrong. Okay, do you guys agree my choice here? I explained my understanding about all the 4 answer choices. Yeah, also the last one, when I say any, like too extreme, sometimes when an answer choice describes something very extreme, it's probably not true. Any question about example 3? All right, very good. Next, also a multiple choice question. Let's see. Which of the following statements are true? Yeah, this one is true. Concerning the mean of the differences between two dependent samples. Okay, means of D. A. If one has 10 matched pairs of sample data, there is a loose requirement that the 10 differences appear to be from a normally distributed population. So sample size is 10 less than 30. So we need a requirement for normality. Even not strictly normally distributed. Roughly, approximately, normally distributed is required. So there's a loose requirement that the 10 differences appear to be, yeah, correct. This is correct. B, if one wants to use a confidence interval to test the claim, mu sub D is bigger than 0. Okay, if the original claim is mu sub D bigger than 0, then the null would be mu sub D equal to 0. Alternative would be mu sub D bigger than 0. At this point, after 2 chapters doing the same thing over and over again, I believe you should get that done very quickly, right? Yeah, original claim is either equal to the null or equal to the alternative. In this case, the original claim is equal to the alternative because the no has to contain equal sign. And we determine the type of the test based on the alternative. Yeah, since the alternative is bigger than 0, it is a right tail test. Since right tail test is a one tail test, remember how do we find the confidence level? On Tuesday, I did stress many times. Is 1 minus 2 alpha. Significance level is 10%. So we would have to multiply twice of 10%. So 1 minus twice of 10% is 80%. It is correct. Why do we have two corrects? A, B, C, D, E. This probably need to choose any correct answer. Yeah, normally if we have 4 answer choices, there's multiple choice question, or there's only one answer is correct. And sometimes when the question give you more than 4, like this one, they probably ask us to choose whatever correct. So B is correct as well for sure. It's something I stressed on Tuesday. It's a one tail test, so we would have to apply this formula to find the confidence level. Because on the right tail of t distribution, we have 10%. In the left tail distribution, we have 10%. And in the middle, we only have 80% that we feel confident about. Let's look at C. The requirement of a simple random sample is satisfied if we have matched pairs of voluntary response data. The first chapter, or first couple chapters of this course, we learned the voluntary response sampling method. We know that's not a good sampling method, and that sampling method will not give us a simple random sample. Simple random sample has even stronger or stricter condition than random sample. Voluntary response not even random, not alone simple random. So C is incorrect. D. If one has more than 5 matched pairs of sample data, one can consider the sample to be large and there is no need to check the normality. No. Either n bigger than 30 or normality satisfy. Even roughly satisfy is satisfying. So this is wrong. This is incorrect. E. The methods used to evaluate the mean of the differences between two dependent variables. Yeah, so mu sub D. The methods used to evaluate the mu sub D apply if one has 97 weights of taxpayers from California and 97 weights of taxpayers from New York City. I would say those two samples are independent. How do you relate to them? Independent. From the information that is given, I do not see any meaningful relationship or inherent relationship between the two samples. So we can't. Yeah, the method we learned today is only for two dependent samples. So E is incorrect. All right, this is pretty good question. Yeah, a lot of information here, especially B. Yeah, please let me know. Am I clear about this question? And do you agree we should choose the A and B here? Especially B. Yeah, do you understand B? If it's two-tailed test, confidence level is 1 minus alpha. But if it's a one-tail test, confidence level is 1 minus 2 alpha. Okay, thank you, Kelly. Well, let's continue. Example 5 is a bigger question here. Yeah, we do have some data, not multiple choice question anymore. Listed below are body temperatures from 5 different subjects measured at 8 a.m., and again at 12 a.m. Yeah, so we do have two samples. This is the first sample. This is the second sample. But we only have 5 subjects. Each subject we measured twice temperature. First time 8 a.m., second time 12 a.m. Find the values of D bar and S sub D. In general, what does mu sub D represent? Okay, this question is about notations. Yeah, very good. Well designed. Well, so this is what we do, okay? Yeah. Yeah, also the question points out the temperature at 8 a.m. is going to be the first sample as I assume S sub 1. And the temperature at 12 a.m. is going to be the second sample. Find the values of D bar. Okay, so the reason the question clarify which one is the first sample, which one is the second sample, because our D is going to be always the first sample value minus the second sample value, not the other way around. Addition and multiplication satisfy commutative property, but subtraction division do not. So we need to be very cautious when it comes to subtraction. We need to be careful which value minus which value, because otherwise you will have a different result. So here we are going to use the first value minus second value, okay? So if we use the first value minus second value, we have this one is a negative 0.6, and this one is also negative because this 99.8 is bigger 0.7 bigger than the first one, and this one is also negative 0.3. This one is a positive 0.2. This one is a negative 0.5. Yeah, so D bar. Yeah, what is D bar? D bar actually is the average of those 5 numbers. You add them up and you divide by 5. Okay, and what is the S sub D? S sub D is the sample standard deviation of the 5 values. I don't know if you still remember the formula. It's gonna be D I minus D bar to the power of 2, and then take the sum of the 5 squares and then divide by 4, then minus 1, 4, and then take the square root. And you know what? I know you don't really want to use the formula, so we are going to use the technology. I'm going to show you how do we use the technology to find those two statistics. Yeah. To me, if the question is only about D bar, I would not use the function. But since it involves S sub D, I think I would use the technology, use the function. Okay, guys, let's go to stat. Edit. And I'm gonna clear all my history information. Yeah, you would see six lists. Yeah, you would see 3, the first 3. If you move to the right, you would see another 3. But we are going to only use L1, L2. I'm going to enter first sample values in L1 and enter second sample values in L2. Okay, let's do that together. First sample is 97.8. Enter 99.1. Oops, make a mistake. Let me do it again. 99.1. 97.8, 99.1, 97.1. 5 values only, so not too bad. And I'm gonna enter the 5 values in sample 2 in L2. Okay, double check your answer. It never hurts to double check your answer, and that won't take too much time. Because if this step you mess up even 1 digit, you will not have the same answer with the correct answer. Okay, seems I have the right thing. Okay, now please move your, how do I say that? Kind of like a cursor, excuse me. Move that to L3. Yeah, you are going to move to L3, but you are going to highlight L3. You are not actually entering values in L3. You are going to highlight L3. So go up one time. Okay, you are highlighting L3. And when you're highlighting L3, you are going to enter L1 minus L2. Okay, how do you enter L1? Second one. The what color that is? Like blue or blue purple, purple blue color. Second one minus second two. Okay? And your L3 will show up. Yeah, right after. So make sure your indicator is highlighting L3. And then when L3 is highlighted, you enter second one minus second two. So on the bottom, you will see L1 minus L2. And then after you hit enter, you will have the following values in L3. Negative 0.6, excuse me, negative 0.7, negative 0.3, 0.2, positive, and negative 0.5, 5 values. Yeah, let me know, do you have the same thing with me at this point? Yeah, my point here is you do not have to manually calculate those differences. Sometimes it's convenient, like this one is not that difficult. Sometimes not convenient. You don't have to. As long as you enter L1, L2, the calculator can do L1 minus L2 for you. Mine says error. Okay, so Miranda, firstly, in L1, do you have the 5 values 97.8, 99.1, 97.1? Yeah, so you have L1 ready, right? Yeah, and then do you have L2 ready? In L2, you should have, okay, awesome. And then now you're gonna shift to the right. You would see at least 3, right? But you shift up once and make sure L3, literally L3 is highlighted. Mine is not colored. My calculator is black and white, kind of like black and white, actually gray. So make sure your L3 is like is highlighted in black. Do you have that? Oh yeah. So make sure L3 is highlighted, and then at this time you are going to enter. You got the answer? Okay, perfect. Okay. Yeah, any other questions, guys? Do you have the same thing? Do you have at least 3 in your same thing? Perfect. Thank you, Kelly. Yeah, list 3 is the sample, is the green sample, okay? Is the differences. Yeah, is the sample of differences of the paired values from the two dependent samples. Okay, so remember D bar is the sample mean of the list 3, right? Yeah, D bar actually sample mean of the list 3. List 3 is our sample. And S sub D is the sample standard deviation of the green sample, the list 3. So what should we do? Remember it's L3, okay? Yeah. Now we're gonna go to stat. Let's go to stat. And then go to the right calc. And then you would see the first one is one variable stats. Yeah, this is from a while ago. Recently, we have used a lot of functions and everything, but this is very basic. Yeah. So conform one variable stats, and then the list. Remember our sample green sample is L3, so you would have to enter L3 there. So second 3 is L3. Second 3 is L3. And then keep frequency list empty and then calculate. I have X bar equals negative 0.38. I have other things like sigma x squared, S sub x. Yeah, S sub x is the one we want. Sample standard deviation is 0.35, 63, 70, 59, 36, 36. Okay, guys, do you have the same result with me? The X bar is our D bar, right? Let's see how do we round it. D bar is going to be rounded to type an integer or decimal, do not round. Okay, we don't have to round it. It's going to be negative 0.38, exactly equal to that. We don't have to round it. S sub D, round to 2 decimal places, so 0.36, rounded up, right? Let's see, do you have the same answer with me? Awesome. You guys are doing great. Perfect. Yeah, that's how do we handle the problem. Find the D bar and S sub D. Yeah, because why do we need that? Because if you manually test the claim using the critical value method, and you want to use the formula to calculate the test statistic. This is test statistic. And you do need a D bar and an S sub D. Yeah, that's the reason. Okay, that's the reason. And you might heard something from what I said. It means we're gonna have technology, right? Yeah, we do. We would have, yeah. But if we use that formula, we wouldn't need to know the values. Okay, so we have one more part of this question. In general, what does mu sub d represent? How about you read the ABCD and let me know which one would you choose for the meaning of a mu sub d? Yeah, knowing it, mu sub d is going to be a parameter, is not a statistic, because parameter describes the population. Statistics describe samples. Yeah, which one is the correct description of mu sub d? You are looking for keyword population, I think. You choose, let's look at both B and C though. C has more people choose C. B says the difference, okay, is gonna be C. Yeah, because mean, population mean, right? Mean of the differences, many Ds from the population of matched pairs. Population is a keyword. A is wrong because A doesn't even have a population. D does have a population, but mean of the means. No, not mean of means. Mean of differences. Difference. B is difference of the population means. Oh, okay. Oh, actually, D is a confusing one. D says actually mu sub 1 minus mu sub 2 is different. Is different. Is interesting though. B means mu sub 1 minus mu sub 2, which is different from mu sub D. Mu sub D is to see it means different thing. Mu sub D is the mean of a new population. If you see the population as the differences of all the pairs from the given two dependent populations. Yeah, this one we should choose C. Very good. Let's look at number 6. As I forecasted earlier, we are going to use critical value method to test the claim. Okay, let's read the question first. Several students were tested for reaction times in thousandths of a second using their right and left hands. Oh, that's a very good paired relationship, right? Same subject, right arm, right hand and left hand. Each value is the elapsed time between the release of a strip of paper and the instant that it is caught by the subject. Results from 5 of the students are included in the graph. Yeah, the sample size is pretty small, right? I would say reaction time is normally distributed, like other measurements of a human being, like blood pressure, pulse rate, weight, height, salary even. Yeah. So results from 5 of the students are included in the graph to the right. Use a alpha equals 5% to test the claim that there is no difference between the two arms, two hands. There's no difference. Okay. So the original claim, there's no difference. No difference means mu sub D not equal to 0. Do you guys agree? There's no difference between reaction of the right. So it seems like right is S1, left is S2. No difference. So yeah. Original claim is mu sub D not equal to 0. Yeah, very good. Thank you, Destin. So the no would be mu sub D equal to 0. An alternative would be mu sub D not equal to 0. So this is a two-tailed test. Two-tailed t-test. Okay. Well, if we use critical value method to test the statistic, to test the claim, we would have to know two things. The first thing is test the statistic t, and the other is the critical values. Okay, yeah. So let's do one at a time. Let's find the critical values first. Simple t distribution. Size is 5. 1, 2, 3, 4, 5. So freedom of degree of freedom is 4. And since it's a two-tailed test, we have alpha over 2 here, which is 2.5%. We have another alpha over 2 here, which is 2.5%. And we are going to have two critical values. Okay, this one is t alpha over 2. This one is a negative t alpha over 2. Since the t distribution is symmetric, centered at 0, we don't really have to do both. We only need to do one, and the other one would be the opposite of the first one. And we are going to do the first one, the negative one. Yeah. How do we find the critical values? We are going to use a critical value is a value, right? Is a score, is a value, not area or percentage or probability. So we're going to use inverse T. Let's go to calculator. Second mode to go back the main menu and the main screen, and then we go to second verse. Second verse. And in the menu, we are going to select inverse T. Number 4. The area must be the area of the region to the left of the critical value. So we are going to enter the area is going to be 2.5%, that is 0.025. 0.025. And the freedom, DF, degree of freedom is 4, right? N minus 1 is 4. N minus 1 is 4. And then paste. I have to enter twice. And it gives me the critical value, negative. Let me see the rounding. Oh, it doesn't have, I didn't include that. Then 2.77644 5098. Yeah, that's the negative critical value. And the positive critical value would be positive 2.77644 5098, right? Yeah. Tell me, guys, do you have the same critical values with me? Awesome. You guys are great. Okay, so we got a critical value. Well, in order to use critical value method to test the to test the claim, we would have to know the test statistic. Yeah, 2 ways to find the T. Either we use the formula D bar minus mu sub D over S sub D divided by root n. Yeah, let me show you the formula right here. Right? Yeah, either we use that formula. Well, in order to use that formula, we have to know D bar and S sub D, right? Well, we are not given those. We don't have it. So I would say we're going to use T tests. Yeah, we need to do that work anyway. So we'd like to use a t-test. Yeah, you would have the p-value, just ignore the p-value. Well, you can use the p-value to double check your answer because they are equivalent. But mainly we are practicing critical value method. So this is what we're going to do, similar with earlier, okay? Let's do it together. Let's go to stat, edit. I'm going to erase all the information from earlier. All the L1, L2, L3. Let me know, do you know how to clear those things? What I do is I highlight L1 on the top and then hit clear and then go down. All the values would be gone. Yeah. So what I would do, similar with earlier, I would store the 5 values in sample 1 in L1. I have 102, 118, 154, 175, 187, and L sub 2. I'm going to store the left-hand reaction time. Yes, 1,000th second. Yeah, in L2. So we have a 115, 135, 180, 199, 202. Yeah, again, double check your answer. Nothing wrong with doing double checking. Okay, so now we go to L3 and go up 1 to highlight L3, and you would enter now you would enter second 1 minus second 2. Okay. On the bottom of the screen, you would see L3 equals L1 minus L2, right? And you hit enter, and you will see the differences, and that's the sample we are going to use to create T or calculate for T. Yeah, calculate for T. All right. So our sample, the sample we are actually used to test the claim is L3. And then what do? We are going to go to stat tests. Now we go to stat tests. And we're going to select t-test. Is a simple t-test. It is a simple t-test. And this time we're going to use data, right? We don't have statistic. We're going to hit data. Confirm, yeah, confirms data. Mu sub 0. Mu sub 0 actually is our claimed mean, the difference, mean of the differences. So it's a 0, okay? It's going to be 0. And is the value in no. Yeah, no is mu sub d equals 0. So you're going to enter mu sub 0 equals 0. And what about list? Remember list 3, right? Now list 1. Frequency list is 1, and it's a two-tailed test. So choose mu not equal to mu sub 0, and then calculate. Let me know did I go too fast, or you want me to repeat that? And you should have t equal to -7.45, 24, 13, 135. Yeah, of course, p-value is there too. Let's just pretend we don't see that because we're practicing critical value method. Do you have the same thing, guys? The reason I do not use the formula is because if I use the formula, I still have to figure out what's D bar and D sub S sub D. I still have to do L3, you know? Of course, use the t-test is faster. Yeah. Same thing. Awesome. Awesome. Very good. Okay. So we are ready to look at the relationship between a statistic and the critical value. Yeah, thank you, Courtney. So our statistic T, let me just round it for convenience. Round it two decimal places, -7.45. How about that? And the critical value, we already have it here. Let me highlight it. It's a critical value. So another critical value, we have 2. Yeah, one is positive, the other is negative. And our test statistic is negative 7-point-ish, way back here. Yeah, way in the left tail. Yeah, negative 7-point-ish is less than the negative critical value. So the test statistic fall in the critical region. Fall in the critical region. Yeah, when the test statistic fall in the critical region, we reject the no. Yeah, we reject no. Yeah, we reject it. Then we would say we have sufficient evidence to support that there. Oh my gosh, hold on. The claim that there is no difference, on my bad, no difference equals 0. Okay, in this case, OC equals H sub 0. Yeah, but doesn't affect other things, okay? It doesn't affect other things. It's still two-tailed test. Yeah, the original claim claims that there's no difference between the reaction times. No difference. So mu sub D equal to 0. No difference. Yeah. So now we reject no. And the no and the original claim is the same. So we can conclude we have sufficient evidence to warrant the rejection of the original claim. So we don't think the two hands have no difference regarding the reaction times. So we are negative about the original claim. All right, does that make sense, guys? Yeah, I apologize again. I'm not going to teach the late night class anymore in the future. Mu sub D equals 0. Yeah, no difference. No difference means.
Well, I do have a question. I know we're practicing critical value theory and stuff, but why are we not using the p-value? Is it there's something against it with the dependent samples?
That's a good question, Kelly. Because on Tuesday we practiced mainly p-value method. We did not use any critical value method. So today we want to just practice critical value method.
Okay.
We want to actually practice.
Sounds good. Just making sure it's not for a specific reason. Thank you.
No specific reason. Well, if there is a specific reason, because this is a question from Pearson, because the Pearson asks you to find the two critical values and the test statistic. It did not ask p-value. So those parts, the question has a few parts. Those parts guide you through the critical value method. It does not mention p-value method. Yeah, of course, we could look at the p-value. We should have the same result, right? My p-value in this case, let me see, what is it? Is very tiny, 0.0017. Yeah, is less than the significance level. So we reject no. We would have the same answer. The thing is, since critical value method and the p-value are always equivalent, and if we use the function, and we normally always get a test statistic and the p-value all together, right? And if we have p-value to compare with the significance level, we would never need to use critical value method. That's the reason I said today we mainly focus on practicing critical value for two reasons. First reason, on Tuesday we did not practice critical value method at all. Second reason, in Pearson, this question is designed to apply the critical value method. All right. Yeah, how about let's use the same question to apply the third method, the confidence interval method. Yeah, I know it's already pretty messed here. Yeah, okay, so that's good. Keep more space, then we can keep going. Yeah, so we are going to apply the confidence interval method. All right, yeah. So let's think what kind of interval function we should apply for this. Sample is given, right? The raw data is given, which in your L3, remember? If we use confidence interval method, yeah, let's go to stat tests. In the menu, what do you think which function we should apply for the interval confidence interval? Do you agree? T-interval? Yes, it's just one sample, okay? We do have 2 samples to start with, but it's actually a one sample. It's just a simple T-interval. Yeah, the test is a simple T-test. The interval is a simple T-interval. Is T-interval. Yeah, exactly. Thank you, Kelly. Yeah. Okay, let's confirm that function. Yeah, T-interval. And then they also give you 2 options, right? Data and stats. We're gonna select data and confirm it. And then, yeah, my L3 is already there, right? So list is L3. Frequency list is 1. C level. Confidence level, guys. What type of test this is? What type of test this is? Two-tailed test, okay? Yeah. Two-tailed test. Since it's a two-tailed test, confidence level equals 1 minus alpha. Okay, if it's a one-tailed test, confidence level equals 1 minus 2 alpha. Yeah, but we have two-tailed test in this case. So our confidence level, what is alpha? Oh, okay, here, 5%. Yeah, alpha is 5%. So 1 minus alpha would be 95%. And that is 0.95. Okay, so let's enter C level as 0.95. Yeah, let me see if you answer the same thing. Awesome. Yeah, 0.95, two-tail. Thank you, Kelly. Yeah. I'm going to, definitely include that for the coming test 4. Yeah. I'm going to make a table. Yeah, this is already a table, right? And add a title for the table. Would it be a good table? So we enter 0.95. No problem. Yeah, that's kind of become our routine. When we're getting closer to the review, I'll recruit questions and formulas. And okay, so my confidence interval is ready. Is negative 26.08, comma negative 11.92. All right, look at that. Do you have the same confidence interval? Yeah, awesome. Thank you, Charlie. Yeah. Where's the 0? Where's the 0? 0 is right here, right? Yeah, way right here. This is 0. So that means, yeah, so mu sub d. So d equals, so the first sample, so that means mu sub d is less than 0. So the confidence interval test can support mu sub d less than 0, actually. Well, anyway, it does not support not equal to 0, right? Yeah, so it doesn't contain 0, so it's against, yeah, will reject the no and the original claim. Yeah, the results are consistent. They do give us the same result. That's the confidence interval method. We have 2 more. Okay. Oh, actually, let me see anything special that we have not covered. It will be similar. It's just different questions. Now this one, yeah, this is a multiple choice question. Yeah, I think they are similar with this question. Yeah, we did this question pretty in detail. How do we find the critical values? How do we find the statistic? Test the statistic. How do we apply the t interval to construct the confidence interval to make a decision about reject no or not? All right, so that's for today. That's for today. Next Tuesday, by the way, we meet at the same time. We do not meet on Thursday, but we meet on Tuesday night. Just make sure you come here for a class. We're going to start chapter 10. All right, guys, I'll say good night now. Oh, let me take a picture of the attendance. Okay. Okay, guys, I'll see you on Tuesday. Have a good weekend. If you have any questions, please feel free to email me. Good night.